Okay.
Yes, yes.
Okay, on behalf of our club Nakshatra IIT Hyderabad, thanks to all of you present here for today's session. It's really a great honor to me having this opportunity to host this kind of webinar session actually. So it's moment of extreme pleasure to welcome our today's speaker, Dr. Saikat Thakur sir, present here to share his knowledge throughout this inspiring talk. Sir is currently the assistant research professor in the Auburn University. He completed his BSc from Calcutta University, India, and MSc from IIT. He get his PhD degree from West Virginia University in plasma physics and the postdoctoral fellow from the California University, San Diego. Working as an associate project scientist in California University, he also awarded many awards like Inclusive Excellence Awards and Diversity Award. His research interest mostly towards to plasma material interaction, let's say plasma diagnostics, plasma spectroscopy, wave instabilities, plasma turbulence, and the nonlinear dynamics and chaos in the plasmas. So today he is going to deliver a talk on how the plasma physics connecting the wonders of the sky to our cell phone kind of things.
Yes. Yes.
So
Well,
please, I humbly request all of you to put mute yourself during the talk. If you have any questions, write in the chat box or you can ask at the end. So with no further delay, sharply, let's invite Dr. Saket to the lecture. Thank you so much, sir. Really
yeah,
means a lot giving us that so much time to us. We are privileged really to hearing from you, sir, managing all the timing and all that. Thank you
yes.
so much, sir. It's over to you, sir.
Yeah, well, thank you. Thank you. I'll like to thank everybody in the Nakshatra Astronomy Club to even, making this club and making this club a big success. It is onto us, students of science, to reach out and include everybody around us into the scientific way of thinking. And today I will just give you a little glimpse of what we do in plasma physics. And, like there are many things. There are many things. I mean, first, I would like this to be just like a storytelling. I am not including any equations. So for a lot of you, it might feel a little boring, and I apologize for that. But I wanted this to be accessible by anybody who is just interested in science. And plasma physics is a relatively not so well known topic. So today I'll just go over some basic concepts of plasma physics. And if you have more detailed questions, definitely at the end, I'll be happy to answer all questions you have, and I can go more detailed into the physics also if you have more detailed questions. But I'll, again, and then, um, yeah, as we go on, this is more like a storytelling. So please put your questions in the chat. I'll be happy to look at them later on, and let's see. So today we will be talking about this thing called plasma physics, right? And I'm sure that not everybody knows about plasma physics much. I had finished I had finished the first year of my master's program in IIT Kanpur even before knowing this word plasma physics. I did not even know what plasma physics is. And yet now I know, I'm more aware that plasma physics is a field that can really connect all the wonderful things we see in the night sky, all the way to industrial applications like our cell phones, which would not have been there without the applications of plasma physics. So with this, I'll start, but I'll even go back even further. Forget plasma physics for a while. Why do we even study science? We are very curious people. We are very curious, species, and there are lots of thoughts and lots of questions. So today I'll pose a set of questions and see if we can answer them. So, in order to, why do we study science? I think, okay, you can say I study science to get a job. I study science because my mom tells me, otherwise it will be bad at home. But more importantly, as a humanity, as a species, we study science to understand natural phenomena in the universe. And if you can see my cursor, I can look at natural phenomena in the universe as a function of different length scales, different sizes, all the way from subatomic particles to cellulars, like cells in biology, to a human length scale, like my height, for example, to Earth systems, to solar systems, to Milky Way, and the visible universe. And this whole gamut, the whole study of science covers these different ranges of scales, going from 10 to the minus 15 to all the way 10 to the minus 27. And different domains of science have actually been developed over history, over the ages to study them, right? So mathematics and logic and philosophy, these are some formal sciences based on which we learn everything else. Then comes physics and chemistry. This is the science of particle physics and thermodynamics, material sciences, material properties. As we go more into that, more into applications of chemistry, the organic chemistry and biology, and our human beings, being a doctor, for example, then even bigger than that is we can study psychology, how we think, and then sociology is like how rules are made, anthropology, how did human beings develop. So this whole realm, today I'll be talking mostly about this small bit of science where physics, where we go from classical physics and we will try to see how astronomy and our regular day-to-day lives get involved via plasma physics. So that is why I had this overview for everyone to understand where we are, what we are talking about today. Okay. And so again, why do we study science? Mainly to explain natural phenomena. But what do we have to do to explain natural phenomena is be a very good observer. So that's what human beings have done. We have been observing the universe throughout our lifetimes, right? And as we do that, we try to understand the systems. We try to understand what is going on. And this word is very important. I say that again and again for every student, for every human being, that we try to quantify what we observe. Casually we say how, something is far, the market is far, or, Hyderabad is far from Delhi or Mumbai or Calcutta. But how far is far? Putting a number is very, very important for us scientists, right? Because as we try to quantify and understand observations, we slowly gain the capability to predict things. We can predict when the next eclipse will occur. We can predict, if we will fall when we jump from the roof of a building. Of course we will, right? And then we verify them through experiments. That is the scientific method. And then what is physics? Where does physics lie in that? Let's think, right? I mean, we always have these questions, like existential questions, because we are curious people. So fundamentally, if we think of physics, to me, it is the study of matter and energy. What is matter? How does it, evolve? What happens to matter? And how does energy get involved in the whole thing? What is matter without energy? All these difficult questions. And then for most of you who are students of physics, you will see that in your curriculum, you will read this big blocks of things like classical mechanics, quantum mechanics, relativistic mechanics, and they're all tied together in a sense that if you are at human or Earth or solar system length scales, and your velocities are in the order of what we see around, the Earth moving around the sun, a bus traveling in front of me, throwing a ball, all these things, standard velocities which are far less than the speed of light. That is the domain of classical mechanics. Now, as we move towards the speed of light, we get to relativistic mechanics. As we go down in length scales towards atomic length scales, we start to get quantum mechanics. Now, quantum field theory is where these two merges, very high velocities and very low sizes, and you get into this whole new field called quantum field theory. And today I'll be talking about plasma physics. See, plasma physics is not here at all. So what is plasma physics in that sense? It's more like, see, all of these domains is applicable to when you have a few number of particles in the system. When the number of particles in a system becomes very, 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 very large, we have to go into this field of thermodynamics. Then we go into this field of fluid dynamics, right? And when all of this come together, when you have large scale systems changing at over time and space, like say the weather. Weather is a phenomenon. It's a very complex emerging phenomena which needs a special way of studying. Plasma physics is also like that. And as we go more towards it, we will learn about it. So physics is a study of states of matter, right? And energy. So what are the different states of matter? And I wish this was more interactive where I could ask you questions and you could raise your hands and answer me. But because of online, so I'm giving you all the answers, right? It's a little boring, I understand, but bear with me. So not only the question is what are the states of matter, but the question also is about why do we call it as different names? Why do we have different names? Why is a solid and the liquid is, why do we Why? There's too many whys. Why do we distinguish between solid and the liquid? Now, in our school, so if any school students are listening to this talk, you would know that, oh, this is an easy question. States of matter, right? What about states of matter? It's solids, liquids, and gases. But then again, the question is, why do we call them different names? So let's see. Let's take an example. Let's take ice. Water or ice is an example which we understand and we can relate to as the different states of matter. So at very low temperature, at temperature I'm equating with energy in this case, at very low temperature or low energies, the atoms and molecules of any substance are kept in the solid phase where they are held tightly in place. So basically, molecules are fixed in the lattice. They cannot move too much. They can vibrate but not move freely. As we increase the temperature or energy of the system, so for example, in water, if it is between 0 and 100 degrees centigrade, it goes into the liquid form. So ice is no longer ice, it's not solid, it goes into the water where the molecules are free to move, right? Because the atomic, that's how they interact. The atoms interact with each other through weak electromagnetic forces. The molecules are free to move. It can encompass a volume. If you put it in a glass, it will fill up the glass, as opposed to ice cubes, which will not fill up the whole glass, right? So what we see already is that the properties of liquids are very different than the properties of solids, and that is the reason we gave a new name to the system of liquids. Now, if we keep on increasing the temperature and the energy of the system even further, the liquid water will start boiling and will produce water vapor, which is in the gaseous state at greater than 100 degrees centigrade, where the molecules are freer to move and intermolecular spacings are very large, and the atoms and molecules are almost unconstrained from each other. That is the gaseous phase. And again, the properties of gases are so different than the properties of solids or liquids that we have to give it a new name. And the thing is, it's not just a name. It's also that when we try to observe, that's the observation, is that the properties are different. When we try to understand them, when we try to predict what is going to happen to them using the laws of physics, we figured out that the same laws that describe a solid might not be applicable when we are in the liquid phase. The liquid phase, which is the hydrodynamics of liquids, all of the same laws might not be necessarily applicable to or enough to describe the gaseous state. We need new gases. We need kinetic theory of gases to explain gaseous states. And then the question lies, what happens when we increase the temperature or the energy of the system even beyond the gaseous phase? Before going into the plasma state, you can already see, because it's up there in front of you, that the next state will be the plasma state. I want to show this range of energies where the molecules start breaking into atoms. It starts dissociating into its component atoms. And if you think, this is the realm of chemistry, right? Where you can break bonds, new reactions can happen, new elements, new molecules, molecular reactions can happen, new components can be formed. And this is the energy scale. Remember, I showed you a picture of science. What is science in terms of the length scales? You can also think of different aspects of science in terms of energy scales. So at lowest energies, you get solids and liquids and gases. At this intermediate energy scale, so thousands of Kelvin, you will be into the realm of what is chemistry. So all chemists and chemical engineers in the world, this is the relevant energies for your systems, right? And as you go to higher and higher energies, once you start to ionize a system, that you can break not just the molecular bonds, but you can actually take an electron off from a neutral atom. You take the electron off, which is negatively charged, and you are left behind with a positively charged nucleus. That is the realm of ionized gases and plasma physics. Now, in plasma physics, when we are in the realm of those energies where you can say a gas has turned into a plasma, that is where free electrons can move amongst positively charged ions, and the positively charged ions can also move around. Now, remember, this is one thing to keep in mind as we move on, that just taking off one electron from an atom might not be the end game. Because you can actually have different degrees of ionization, right? If you have a heavy element like, say, argon, which has many electrons in its outer shells. Now, if you have something called like hydrogen, you take off a single electron, it's fully ionized. But for argon, for example, you can have many levels of ionization. You can take off 1, 2, 3, 4, multiple electrons. right? So sometimes you have partially ionized plasmas, and sometimes you can have fully ionized plasmas. Okay. So basically, the energy state beyond where chemistry happens, the energy state where you can have freely moving electrons and ions in a system. So you start from a gas and then you increase the energy so it can have freely moving electrons and ions in that system, will be called the plasma state. And again, is there the necessity to give it a new name? Can I just call it hot gases? Now, what we find is, and as we go in this talk, we'll find that the plasmas, ionized gases, have very different properties than regular normal gases. So kinetic theory of gases are not enough, not sufficient to explain the phenomena that we can find in plasmas. And because, as you can already imagine, that they have charged particles. So it will behave like a gas sometimes, but they also have charged particles. So now I can use electricity and magnetism. Electric and magnetic fields can affect plasmas, while electric and magnetic field cannot affect gases, right? And so that is kind of what plasmas are. And okay, now that we have a slight thought processes of what is plasmas. I mean, I hesitate to say we know what plasmas are because I am also still learning, right? The learning process never ends. Let us see if we can think of some naturally occurring plasmas. I mean, usually this is a very nice it's a nice icebreaker, a nice game you can play when you have students in front of you or audience in front of you, but unfortunately, it's an online talk. So I'll give you the example. Lightning is a naturally occurring plasmas on earth. You see, when you have like a large amount of electricity going from one cloud to another, or going from the cloud to one of these buildings or your airplane, that high current actually heats up the gas that is in the path of the current. The temperature can go so high that momentarily it can ionize the gas and bring it to the plasma state, right? Now you can also say, questions and questions and questions, more and more questions. As we think more as human beings, right? As scientists, we have more questions. Why is lightning temporary? Why doesn't lightning happen all the time? This is because as the current flows away, the temperature drops. And as the temperature drops, you cannot have ionization of the gas, and hence you are back into the gaseous state. So here we see examples of plasmas momentarily, right? Another example of plasmas on Earth are aurora. It's kind of unfortunate that India is way far south in the latitude that you cannot see auroras in the sky. But if you happen to go to Alaska or Greenland or Norway or Antarctica, so the North Poles and the South Poles of the Earth, you find these beautifully large scale variations of beautiful colors in the sky. And these are called auroras. And then again, you ask, why do auroras happen? What is it actually happening? So actually, highly energetic ionized particles, which is again plasma, from the sun, it comes all the way to the earth. And as it hits the upper atmosphere, it can ionize the gases that are in the upper atmosphere. It could be nitrogen or oxygen or carbon dioxide, and produce these brilliant colors, which the formation of colors again belongs to chemistry. So that's also different levels of energies that we are working with. And another funny thing, again, questions and questions and questions. You find, why is it only around the North Pole and the South Pole? Why not near the equator? Why not from Hyderabad, right? And again, we'll have answers to that, because we know that the Earth is a big magnetic field with the North Pole and the South Pole near our poles, and there's something to do with the magnetic fields. Let's see. So before we go to understanding all the details of plasmas, why are plasmas so rare on Earth, right? And I gave you the answer. The Earth is too cold, because, as I said, you need to go to that particular energy states to ionize gases like strongly enough or in large quantities enough to get electromagnetic effects. That's when we call it plasmas. And the Earth is too cold. Thankfully, good for us, because hence biology can happen and human beings could be born. And but because the Earth does not have so many examples of plasmas, that's also another reason why it's not a very well-known topic of studying in our undergraduate curriculum. We study solids and liquids and gases, but we don't study about plasmas too much because we don't find them much. And but since they're so rare on Earth, let's go out and explore. Let's explore, what's around us. So the first thing, as we go away from the Earth's surface, okay, so this is the height of Mount Everest. and this is the layer in which ozone. These are the different layers of our atmosphere as we go up. You see, this is the altitude given in kilometers, and so we see different bands of iron structures. And this is the ionosphere. The ionosphere starts around, like, 85 kilometers ish. And what we see is that the temperature actually goes up very high. Now, as we go from the surface of the earth, the temperature goes down initially, but then it has different zones, and in the ionosphere the temperatures are very high. At the same time, the pressures are very low. This is the normal atmospheric pressure, but the pressures are low. So ionosphere is a region where it's very hot, very lonely. There's not a lot of things over there, but you only have electrons. You have lots of electrons and ions in these ranges. And it's very important, it's crucial for our modern day, because it's the using the electric field, or the ions of the ionosphere, we use it to bounce back radio signals. So without the ionosphere, we cannot actually send radio waves all around the earth. And it's interesting and funny that every plasma system that we deal with have direct consequences to our modern era or modern life. So going beyond the ionosphere, let's talk about the magnetosphere. We know that the earth is a giant magnetic field. Earth has a giant magnetic field, it's a magnetic. And the magnetosphere is this bubble of magnetic field around us. And so this is an artist's representation of the bubble of magnetic field around us. Now you'll say, the magnetic field is not as symmetric. If you think of a dipole, the magnetic field happens very nice and symmetrical. But here you see lots of asymmetries, as if the magnetic field is squished and stretched on one side. Why is that? That's because of something called the solar wind. And where does the solar wind come from? I gave it away. It comes from the sun. It's solar wind, right? As if the sun is blowing a wind on the Earth's magnetic field. What is the solar wind? That's also another example of plasma. And if we look at the sun, right, it's because it's the solar wind comes from the sun. So if we look at the sun, that's our closest star. It is nothing but a big ball of plasma. So there are different ways of looking at the sun and try to understand it. So one thing I wonder, that even before we had all these technical details of studying science, going to college and stuff, like age old, let's go back to the dawn of civilization. Looking up at the night sky, we saw the stars, right? These little bits of light that we can see only at night. During the day, it's overwhelmed. We don't see anything in the sky other than the bright sun. And then we have been wondering throughout our history of humankind, like, what is the sun? What are the stars and stuff like that, right? And then let's observe some events on the sun. So these are sun, and people have also seen little sunspots. So what are these sunspots? Actually, if you look at, there's a visible image, you see the sunspot. If you look at the X-ray image, you see like stuff coming out explosively from the edge of the, from the sun. Those are the sunspots actually. And if you look at the sun on the edge, you can see these huge structures come out from the sun. And I like to, so these are effectively, you can have solar flares. So you can have solar flares, which are little bubbles of plasma that come out from the sun. And if our luck is not good, it can actually face the earth. And these are two representations to show you the length scale, the sizes of these solar flares. This is the size of Earth. Can you imagine? The Earth is so infinite, so small with respect to these humongously large solar flares. And then you can say, why don't we get fried? Because two things: when the size of the Earth represented here is correct, but at this scale of the sun, the Earth is not so close to the sun. The Earth is actually far, far, far away. And also the Earth is a small little dot revolving around the sun. So these explosive events that happen on the surface of the sun not necessarily faces the Earth. So these solar flares are not always coming towards the Earth. Sometimes they do. And you will hear in the news, you will hear in the online news or something that, a big solar storm is coming, a solar flare is happening, right? And now it's not necessarily dangerous to people on the surface of the Earth. But why? It's because of the magnetospheric plasma. So the magnetosphere, which is the bubble of magnetic field around the Earth, and it contains charged particles. So we have magnetospheric plasmas. So when you have these little bursts of plasma from the surface of the sun coming towards us, this produces the solar wind, which is plasma coming out from the sun, traveling all the way from the sun to the Earth. But then it interacts with the magnetic field around the Earth. See, it is this force, is this pressure, which distorts the magnetic field around the Earth into an asymmetric, structure where the sunward side, like the part of the Earth facing the sun, the magnetic field gets compressed. The the night side of the Earth, the magnetic fields get extended long back, and but this does not allow all the harmful, highly energetic particles from the sun to come directly all the way to the Earth's surface. And voila, plasma again saves us, right? And but you also look at this and you think another thing. So these are charged particles, and around a magnetic field, charged particles will go round and round. It will gyrate around the magnetic field. So these charged particles actually hit the upper magnetosphere of the Earth and follow the magnetic field lines, and it would go towards the north poles and the south poles of the Earth, following the field lines, because Earth is a dipole. And that is why you have the auroras near the more north poles and the south poles. So this is a wonderful, like how the Earth and the sun is connected via plasmas, right? So you have an explosive event from the sun, it comes all the way to the Earth, and then the Earth's magnetic field redirects it around to the north poles and the south poles of the Earth. And when those energetic particles from the sun, the plasma from the sun, interacts with the upper atmosphere, that's when you have the aurora. So this is a wonderful phenomena. But at the same time, you have to understand. Actually, I'm sorry, I apologize that I had many more slides, and my original PowerPoint presentation crashed at like 9:15, and so I couldn't show you all the detailed pictures I wanted to show you. I might send that to you guys later on. But let me just say that this phenomena, as beautiful as it is for the phenomena of seeing the aurora, this can be very harmful to all the satellites that are actually surrounding the Earth, and all the electronic grids and the electronic structures that are on Earth's surface, because this humongous energy coming from the sun in the form of a solar storm can destroy the satellites. And now our modern life depends so much on satellites. The whole system of GPS. Without GPS, so many people cannot drive anymore. And telecommunication. This is all depend on all the satellites that are going around the Earth. So this is actually a very crucial and a very important topic that NASA and the European Space Agency and ISRO, they're all worried about. And again, if a lot of young students, I'm guessing, are listening to this talk, and if you're interested in like space plasma, solar plasma, magnetospheric plasmas, telecommunication satellites, this is a field that I think in the next 30 to 40 or 50 years will be humongously important for us. NASA has whole different sections dedicated to something called space weather and predictions of space weather, because it is so crucial to our survival. And every dangerous thing, we try to, again, I said science. In science, we try to understand and predict. So we're trying to understand, we're trying to predict, just like predicting the next, cyclone, predicting the next thunderstorm, and moving people away from harm's path. Similarly, we have to understand and space weather and try to save the satellites around the Earth, because they are above the Earth's ionosphere, right? And so, or the Earth's magnetosphere. So this is a very important field, and going forward in the next 30, 40, 50 years, I'm guessing, I'm sure that many of you will find a very satisfying career working in this field. Now, going beyond the Earth, right? We have our whole solar system, and as I said, every time, every human being since the dawn of civilization looked up to the night sky, has been amazed by the stars in the sky. This very tiny but twinkling lights that come every night, they slowly move over the night. What are they? It inspires awe. And I'm actually sad that the modern life, the amount of lights we have in the cities or any big city, prevents us from sharing and being a part of this awe and the wonder of the night sky. I would really request, if you can, if you go for a vacation, or you go to your ancestral village or something, try to look up at the sky at night. It's the dark skies with the twinkling lights gives you a wonderful sense of who we are and our connection with nature. So this is a picture of, there are these dark spaces in many places in this world where you can go and do astrophotography. You can actually point your cameras to the stars and take pictures. You can take pictures with a long shot, like you can integrate the light over a longer time, and then you can get beautiful pictures of the Milky Way galaxies. And this is one of them. But then now we know that as all the stars are just suns, right? The sun is happens to be the nearest star, and we are in the solar system. But all the stars are like sun, or different from the sun, but it have the similar composition and the similar way of producing the light. And these are pictures of, okay, of course, no one went up and took a picture, with a small camera, but this is the rendition of what we understand, like of the scale and width and breadth of the Milky Way galaxy, right? It's about, 100,000 light years wide, millions of stars in that, right? And this is the approximate position of the sun. And from the side, the Milky Way galaxy is kind of, it's a spiral galaxy, and you can see it's like a planar. And you might again wonder, why is this shape? Now, see, galaxies are rotating. When you have a bunch of fluid-like things rotating, say while making a pizza or making a rumali roti, right? As you take a dough and rotate it, the angular momentum makes the thing go flat and wide and like a spiral shape. And again in the detailed studies of very exoteric and exotic physics stuff, you will find that your basic physics that you learn in your school is will come up again and again. And this is another example, but going back to our connection of plasma physics, each of the stars are like a sun. So each of the stars are nothing but plasmas. So when we look at the night sky, you see plasmas all the time, right? And going all the way back to the Eagle Nebula, the stellar clusters, like these are basically ionized gases where stars form. These are the formation and the birthplace of stars. So, and they are nothing but examples of plasma systems. And because these are charged gases, gases are not neutral, they are charged, and they interact via electromagnetic effects. And hence, these are all examples of plasma systems. So, so in a sense, that yes, when we look at the Earth, we don't see much examples of plasmas, right? And yet 99% of our visible universe is actually filled with plasmas. You can go all the way from lightning, which we see on a daily basis, aurora, right, which are exotic events that happen near the poles of the Earth, to this, as I explained, that this solar flare that comes from the sun interacts with the Earth's magnetosphere, produces this beautiful aurora, all the way to the stars and galaxies and star formation. I mean, the universe is teeming with examples of plasmas, and plasma phenomena, and understanding plasma phenomena is so crucial to understanding astrophysical phenomena. And probably before moving ahead, I would like to say that again, I'm sorry, my previous presentation crashed. I couldn't show you all the cool pictures, but I'll figure out a way of sending them to you. But you can go online. So I request, everybody, we are curious people. Everyone is just very curious to learn more about nature. And now most of us have internet almost free with us, right? So Google in, whenever you Google in, like, star formation, astrophysical phenomena, what you will find is lots and lots of very awe-inspiring pictures, very recently. So our best diagnostics to look at space, astronomical events and study them was the Hubble Space Telescope. And now we have the James Webb Space Telescope, right? Very recently sent. And it's been a very, very, very exciting times for, astronomers, astrophysicists. Now, whenever you see this phenomenon and all the pictures and images from James Webb Telescope, just remind yourself, these are all examples of plasma, very special cases of plasmas. And even the black hole, when you see the picture of the black hole, it's been a very famous picture now, right? It has been everywhere on the news, on websites. What you actually see, you don't see a black hole. You see the silhouette. You see the plasma emission around the black hole, and you don't see plasma emission from the black hole. You see it around it. And that's why through the plasma emission, you can guess the picture of the black hole, right? Once you start thinking about it, plasmas are everywhere. You just cannot avoid it. And so anyways, as we see that all the way from the astrophysical events to the ionosphere, and once in a while on Earth, plasmas are there. But as I said, why are plasmas so rare on Earth? Because the Earth is way too cold for plasmas to naturally occur. You can think of it similar to if we open the freezer, we call it the deep freeze, right? The top part of a freeze. Why is there no running water? You have ice, but there's no running water, right? Why is there no running water? Because it is very cold. It's too cold for the running water state of matter to exist. At the temperatures and energies in a deep freeze, in a freezer, what we get is only the solid state of water. And that is similar to on Earth, the temperatures are so cold that we get the solid, liquid, and gaseous phases of matter occurring naturally. But then again, questions, then why do we care? I mean, why do we care? The reason we care is that the Earth, in the industry, there are tons and tons and tons of examples of how we have learned and understood how to make plasmas, and then we use them industrially in technology. So artificially made plasmas have actually changed humankind and human life. All the different kinds of emissive lights that you see, if you go to any big city, it's teeming with lights. They couldn't have, many of those lights couldn't have been there without understanding plasmas and plasma phenomena in the laboratory. And these are some examples nowadays. So this is lighting, right? And then nowadays plasma TV is becoming more and more common. It's coming out in, like, it's a commercial thing now. It's no longer in being developed only in the labs and studied only in the labs. It's more commercial, and you might be having one at your home, and it works with the principles of plasma and plasma light emission. This is one of the greatest technological advancements of humankind, I would say, that the semiconductor etching, that you can take silicon, and using plasma systems in a plasma setup, you can actually etch very, very fine grooves. See, these are in the order of nanometers. Nanometers are like thinner than our human hair. But it is this technological advancement that have allowed us to make like semiconductor transistors very, very, very small. And if you think about it, that in the 1970s and 80s, people knew how to build a computer. The process of using digital technology, people knew about it in the 50s and 60s. But those computers were huge. 100 megabyte computer, like memory, would take like the space of several cabinets. It will fill up a room, right, in those days. And that was before the technological advantages of plasma manufacturing. Plasma manufacturing was discovered and studied mostly in the 1970s and 80s. And as plasma manufacturing, the quality of plasma manufacturing increased as a function of time, the sizes of computers become smaller and smaller and smaller until you have one computer at your hand nowadays, which is a cell phone. Like, a cell phone is almost as good as a computer. It can connect you through Wi-Fi to the whole world, and you can see cool pictures of plasma phenomena, right? But so this is a humongous achievement of human technology, and unfortunately we don't know it that much. Going over to more medical and biological aspects of plasma physics, in the lab, again, we are curious people, and we try to do new things. We could actually figure out how to reduce the gas temperature, the surrounding temperature of surrounding the plasmas, and make them cold enough. See, until now I was talking of high temperature plasmas, right? But you make them cold enough that you can actually put a finger. And I don't know if this is the finger of a professor. I'm guessing it's the finger of a graduate student, but whatever. But so that the plasmas can actually touch your hand. We also have similar examples of plasmas in our lab, and this is becoming more and more common. Many labs in India work on plasma physics, and you can actually have real life applications of plasma medicine and plasma sterilization, and this is the whole field of cold atmospheric plasmas. Now, of course, no technology develops without studying them in the lab first. So we do laboratory experiments. Plasmas are used for space propulsion. We use plasma thrusters, like Hall effect thrusters actually, and we are also trying to devise new methods of electrode-less, contact-less thrusters for space applications and space propulsions. So we can actually go to beyond Mars. We can go to like Pluto. And another big huge aspect is thermonuclear fusion, where we are trying to make a small star on Earth. And there are different aspects of thermonuclear fusion. One is magnetic confinement, and the other is inertial fusion, where you can have a momentary reaction nuclear reaction to produce energy, where the energy is confined using like many lasers focused at one point. So it's the power of lasers that can produce the fusion, where it is the here the confinement is coming from magnets and magnetic fields around the toroidal device. Now, in my mind, I mean, each of these phenomena can have its own talks, but I just wanted to give you a glimpse of why, in spite of the fact that plasmas are so rare on Earth, naturally occurring, but our lives depend on plasmas every moment, every day. And so by now, I think I've given you a little idea of the fact that it's we might call plasmas the fourth state of matter because we know three already, like solid, liquids, and gases. Three gone, so it's the fourth. But it is the most abundant one. Like 99% of the visible universe is made out of plasmas. And we just happen to be in this domain where solid, liquids, and gases occur because it's too cold and too dense for classical plasmas to exist. I mean, but then we still try to fight with nature to do artificial plasmas and get into this domain. But this is a very nice picture, for all of you in like interested in science, and again, as I said, it's important to put numbers. It's important to quantify something. So this gives you the range of number densities. As you see, this is in the logarithmic scale, right? 10 to the 3 to all the way to 10 to the 33, and then range of temperature. So it's always this is what defines the density of matter, and this is defines the energy content of what you are working with. This is the temperature scales all the way. This is the range where plasmas exist. Now, understanding that these are just examples of plasma. Now, if we think, again, why are they not gases? Is that they can be either fully ionized. So if you have hydrogen and you take off one electron away from hydrogen atom, a molecule, you get fully ionized, plasmas. And so in the solar system, in the solar plasma, you have fully ionized. You can have fully ionized plasmas. In fusion devices where you use hydrogen, you can have fully ionized plasmas. I mean, most laboratory experiments we use gases, inert gases like argon and neon and helium or xenon, and we ionize them to the first degree. Like we take off one electron, and that's partially ionized. Also, we have to remember the neutrals are present. Not if we have 100% of the gas might not be ionized. It can be only partially ionized, and still it can be into the plasma state, as long as the ions and electrons have densities high enough that this is a technical term called Debye shielding. That means if you have a charged particle in the plasma, because plasmas have freely flowing electrons and ions, electrons will come faster to the charged particle or anything that you put into the plasma, and it will collect more and more particles near the system, so that far away you actually lose the information that there is a disturbance in the system. And this kind of an effect is called Debye shielding. You find Debye shieldings in many places, like even in polar liquids. Whenever there is charge and charge distributions, you actually find the effect of Debye shielding also on human beings. And whenever there are a large number of particles, you can actually have this phenomena of shielding. Say if there is a small accident on the road, or if somebody falls down on the road, a lot of people will suddenly come together and try to help them out. But far away from there, the information doesn't travel. You don't know. So basically, a small group of people or ions or electrons, objects can actually shield the phenomena. So if the electron or ion densities in a system are high enough that you see the phenomena of Debye shielding, that is when technically we would start calling that system a plasma. And so this is where we start differentiating the properties of gases and plasmas. And because of this, Debye shielding cannot happen if you have only one or two particles, or if you have one or two people trying to help out. So you need a little crowd, and that is coming only when the densities are high enough. And because of that, you get this thing called collective effects. And since you have charged particles and the large number of charged particles, you can have long range interactions, electromagnetic interactions, as opposed to nuclear interactions, which happen at a very short spatial scale. And these collective effects and long range interactions are important for plasmas, for something to be defined as plasmas. And of course, plasmas will react to external electric or magnetic fields. This is also how it's different from gases, just to bring you the thing. Now, since we have a little more time, maybe like 15 minutes or so, I would like to talk about some very exotic form of plasmas called dusty plasmas, because that's what we do in our lab. And let's see if I can explain that to you. So if you have small bits of solid particles immersed in a plasma system, and I'll tell you why, this is very common in nature. So we call that a dust particle. So this is a solid particle immersed in plasma. What happens is, because of this phenomenon of collective, interactions, like this collective phenomena, collective effects, and device shielding, we have very strange phenomena that it will gather more electrons, because electrons are very light and it can travel faster than ions, and this will become charged. So the interaction of a material, of a solid material, which we call the dust, in the plasma, with the plasma will make it charged. So now when you have lots and lots of charged particles floating around in the plasma, you can get different kinds of very interesting phenomena. And it's interesting and also important because it happens in nature. So dusty plasmas are actually very complex systems which has ions and electrons and neutral atoms, because not all neutrals are ionized, right? And you have dust particles. And the plasma dust interaction is via charging, and you can get different kinds of collective phenomena. You can actually see, this is dust particles floating in the middle of a plasma chamber. And we have shown a laser light. This is a green laser over which you can see this wave phenomena, and you can see particles moving around, and you can see this is a very you can see the difference between bigger particles and thinner particles. The smaller particles are actually floating higher up, and you have this little streak which is and it's a very complex phenomena that we are trying to understand. And let's see if we so and the reason we study that is dusty plasmas occur everywhere in space and the lab and the industry. When I said that there are many examples of plasmas, in all the examples of plasmas you also have dusty plasmas, because you also have solid particles floating. So this is all the way to the nebula. As I said, this is the place where stars are born. So even in the stars birthplace, you have dusty plasmas. This is the rings of Saturn. And you can see rings of Saturn are actually small bits of particles floating around. And as I said, the solar wind, the solar from the sun, it comes and encompasses, it surrounds us. We are surrounded in plasmas. And so the intergalactic space is filled with ionized charged particles, which is plasmas. And you can see these small particles gather together, form a structure, and they are all charged. And you can have striations. These streaks that form in the middle of dusty plasmas can also be found in the rings of Saturn. And this is a comet. So we knew comets have a tail. I had no idea until studying plasma physics that comets actually have two tails. And this is one of the so this is actually a zoomed in picture of a comet. But there are also examples of dusty plasma. You have noctilucent clouds. And then the surface of the moon. One reason why going back to the moon is for human exploration is very hard, because the surface of the moon is covered with dust, and the ultraviolet rays from the sun. Now the moon doesn't have an atmosphere, or it doesn't have its own strong magnetic field like it doesn't have a strong magnetosphere like the Earth. So UV rays and all the plasmas coming out from the sun affects the moon, and the surface of the moon is covered with dusty plasmas. And there are pictures of human beings coming back from the moon, right? Neil Armstrong, and when they came back from the moon, their space suits looked like as if they're coming back from a coal mine. They're that bad. And even in our lab, we work with NASA to try to understand lunar dust, and how can we prevent lunar dust from contaminating the body suits of astronauts going back to the moon. You know from news probably that very recently we sent a unmanned spacecraft to moon, the Orion, and in a couple of years we are probably trying to go back to the moon. Now coming closer to home, like in plasma manufacturing, you see these blue regions are actually, this is a laser coming and illuminating the dust around the semiconductor devices. So this is similar to the dusty plasma that we see in our laboratory, right? But if you cannot get rid of them, this dust will fall back when you turn off the plasma to take out the integrated circuits. So it's extremely important, and plasma manufacturing companies have spent millions of dollars in order to understand and study and remove dust. And of course, we do fundamental physics. So in a nutshell, before I open up to questions and stuff, natural and artificial plasmas occur at multiple scales, from nanometer regimes to light year regimes, all the way from manufacturing to the experiments and energy producing methods that we are trying, lightning and the aurora and the space weather, so space plasma, all the way to astrophysical jets and star formation, and all of them have dust in them. This is just to reiterate them. And I might stop whenever we want to, but this is just a glimpse of the laboratory that we have. And again, different phenomena, the magnetized dusty plasma phenomena, space phenomena, and small laboratories which are these are owned by each grad student. They have their own machines, and all the way to atmospheric plasma jets and stuff like that. These are our bigger devices, and a host of signatures, and there's a host of things studied. I want to tell a little bit about myself because okay, I'm from Durgapur in West Bengal, and a small industrial township, right? And I just wanted to tell you that there are lots and lots and lots of interesting things to study in the field of plasma physics, in any field that you are interested in. And just keep hope, keep perseverance, keep on studying, look out for interesting opportunities. Try to go to a research lab, try to talk to a scientist in your neighborhood or in the city that you are close to. Try to go to their labs, see what they do, talk to us. We would be so happy when students talk to us, and we would definitely try to play a part in you becoming successful. And we need lots and lots of good scientists going into the future. And again, if I could come out from a very small industrial town in India, um, and being the first in my family to do that, my parents were not in science, not in physics, nothing. And and you can be a part, just like I am a part of understanding and studying plasma physics, or anything that interests you. You can be a part of that. And so with that, I would probably stop and take questions.
Yeah, thank you so much, sir. Actually, it's really nice talk
Yeah,
because we can at least connect with the things like you told how far and how it's the dust in the whole kind of nature. So there are a couple of questions I am going to read. Could you please answer that?
absolutely.
Yeah.
Hmm.
Mm.
Very nice talk.
Thank you, thank you,
Very nice talk.
thank you.
Please
So
explain that dust acoustic shocks wave.
Well, I don't know if I want to go into the details of any physical system. I'll give you a hand wave because I don't have equations or anything. Just this is just like a storytelling. And so what happens is, like when you have a large collection of particles, right, in anywhere, in any
Yes,
system, and you give it a perturbation, what happens to that, right? It's like molecules in the air. When you perturb molecules in
yes,
the air, it gives a perturbation. It can take particles away from its own like original state of equilibrium, but then there are always restitution forces that bring it back. It's like a pendulum happening, right? There would be interacting forces that tries to bring it back, it overshoots. So what you end up doing is, using that perturbation, you end up actually making a wave, and the wave can propagate depending on the specific conditions. And so in a dusty plasma, you can think of dusty plasmas as a system where you have many particles, but they're all charged. So in addition to understanding what we understand as a simple acoustic wave, so sound wave is an acoustic wave, right? And it
yes,
travels at the
yes,
speed of sound. So it's a similar phenomena, you can think of that, but it's happening with charged particles as opposed to neutral particles.
yes,
Phenomenologically, it's not very different. The difference comes in how the restituting force, like what brings it back. If I push something, why doesn't it just go away? So it comes back and it sets up the wave. But I probably I can probably give you more details about like technical details. I can email you, and if you want to. But since this is a very public talk, I don't want to bore everyone, and I would rather want everyone to stay till the end and just talk and discuss and throw all sorts of questions.
thank you, thank you.
okay, sir. Johan Sharma asked, in case of dusty plasma, is
Mhm.
the quasi neutrally still maintained locally?
So very important question, but it is not one single question, it's many questions. What do you mean by locally?
Selectively.
Yeah, so it's no, this is very nice, as just normal human beings, as curious human beings, and when you are going deep into the physics aspects or the science aspects, you have questions, but then questions are sometimes simple sounding questions becomes very complicated and research topics, because there are questions at every level. So quasi neutrality, if I understand correctly, quasi neutrality is the question. So quasi neutrality is something that occurs at a larger spatial scales. So when you look at the plasma over a large scale, you expect that the same number of positive and negative charges happen. That's why when you have dust in the system, so if you don't have dust in a system, you just have electrons and ions, you have almost the same number of them. When you put dust, it collects the electrons preferentially, it collects more electrons than ions. And so dust can actually change the number density of electrons and ions in the plasma. Dust affects plasma. So, and they affect each other. Now, when you say locally, how local? Inside the Debye shield forms because of deviation from quasi-neutrality. That's why it is called quasi, right? It's not exact neutrality. So the Debye shielding is when you have particles coming and clustering together, and in that it's preferentially more electrons, and that's why you have the dust charging as negative. Now, again, this is a generalized, more common phenomena. There can be exotic phenomena all the time. So the lunar dust, the dust in the surface of the moon, that gets the brunt of ultraviolet rays from the sun, and it can actually charge positive. So there are all these technical details that we can go into. It can, depending on the context. So context is also important. But again, when you say locally, so inside the Debye sphere, you will not get quasi-neutrality, right? That's the whole definition of a Debye sphere, that outside it, you will start to getting quasi-neutrality. But in the bulk plasma, even in the case of a dusty plasma system, we do use the concepts of quasi-neutrality. So when the positive and the negative charges add up to almost zero globally. Yes.
Okay. Sir, and one question from my side. I don't know that much about plasma, but as I see some lectures, there is some using the laser beam, we can cool that plasma also. Let's say in the state of Bose-Einstein condensation. So when do you have any technique in your lab or some kind of that laser setting that we can cool also plasma in that very low temperature?
Right. So in our lab, the answer is no. In our lab, we don't do laser cooling of plasmas, but there are labs in the world who actually do that. It's a wonderful field of studies. There are labs, some labs in Houston, I think Rice University, and some labs in Colorado, University of Colorado at Boulder. They specialize on laser cooling of plasmas to the temperature where it is really, you can start to see that collective effects of very cold. Like very cold they call it ultra cold plasmas, where the plasma temperature, I've been talking of that in thermonuclear fusion or in the stars, the temperatures are in millions of Kelvin, right? But you can go down, you can take the temperature down through laser cooling and more technical methods than I am aware of, probably, that it goes into the millikelvin, it goes into the Kelvin scale, and
Yes, sir,
probably there you can.
exactly. So I am thinking that laser is the thing where we can do the very low temperature cooling and also heating. So both at the same time we can do with any laser beam.
Right. So what happens is, again, very important question. See, it again warrants the question, like, what do we understand as temperature? What is temperature, right? I mean, temperature is not just what we put the thermometer in my mouth when I am sick, right? But what does it exactly mean? It's all about the vibrations and the energy of particles, right? So if you can if you have charged particles, that's the fun part about charged particles, right? And what is light? Light is nothing but electromagnetic waves. So if you can trap charged particles within electromagnetic waves, effectively you don't allow the particle to move around very fast. And that is another way of reducing the kinetic energy of the particles. And if you try to measure the kinetic energy, it would be like very small. So you can use lasers to, it's a wonderful tool. You can use lasers to do whatever you want, kind of like heat up, like you can do laser fusion, but one thing you have to keep in mind, it's not the same laser. It has to be a different laser, because you can think of it as, you can use a hammer to break things apart, but you can use a chisel along with a hammer to actually mold structures and make beautiful shapes and temples and
Yeah,
right.
exactly. Thank you
So,
so much.
so different things have different domains of applicability, and as long as you understand that, it's actually amazing.
Okay. So Deva
Sir, I
Bhatta
have a
asked, is
question.
dirty plasma found the mesosphere of the Earth?
Yeah, so dusty plasmas can be found in almost all the examples where you have plasmas, because of a couple of things. One is that it's very hard to ionize a system fully 100%. Like you take a bunch of gas, right? You apply energy to it, and only in very special circumstances you have all of the neutral molecules, neutral atoms changing into ions. So you always end up getting a mixture of states. You have some gas neutral particles, and you have this always some phenomena or the other producing solid particles nearby, and it's very hard to get rid of uh, in that sense, like dusty plasmas. So again it will boil down to what I said in the beginning, that a lot of details boil down to numbers and putting numbers, quantification. Now, is the number of dust particles or like solid particles in a plasma high enough to distort the characteristics or change the characteristics? That will define whether we would call it a dusty plasma or not a dusty plasma, and so on. Because you can have dust floating in plasma but not changing the characteristics, then we actually technically don't call it dusty plasma, but we call it dust in plasmas.
Okay, so Poppy asked, in solar flares or solar winds, is there only ions and electrons or some other particles also present? And one more, in plasma there is two species, but in dusty plasma the dust particle size may be large compared to ions. So in this plasma there will be three species.
So very good questions. Actually, I did not go into all the details. So, but you're right. You're absolutely right. So not just three species. So in the general plasma systems, you usually have ions and electrons and neutral gases. In very specialized cases, all the gas, atoms and atoms will be ionized, where you have only ions and electrons. Usually you have ions, electrons, and partially magnetized plasmas are the general rule. The fully ionized plasmas are the exception, but you have ions, electrons, and gas particles. Now, in dusty plasmas, yes, you have solid, or sometimes you can also have liquid particles. Like you can have aerosol. If you are spraying something in the plasma, that those little droplets, when it is moving through the plasma, will also gather charge and become charged and become dusty plasma like. So in dusty plasmas, usually you have four, like ions, electrons, dust, I mean the solid particles or the liquid particles, and gases, neutrals, basically neutrals that have not yet been ionized. Now, another thing which you mentioned about the size is absolutely true. Ions typically, if you think of ions, say I think of hydrogen ion, the lightest element, right? The hydrogen ion is about 1800 times, like 1836 or 1876, something like that, like 1800 times heavier, more massive than the electron, right? When we use say let's say it's 2000, in the ballpark. When we use argon plasmas in the lab, that means argon ions are 80,000 times heavier than the electron. And what it does is it changes the time scales of motion around electric and magnetic field. It changes its thermal motion, it changes in its frequencies and of gyration, the length scales of gyration. Is it gyrating in a very small place, is it gyrating in a large radius? And now the dusts are massive. Dust can be, millions of times heavier than the ions. So dust in itself is a completely different, I would say, like a beast. It's a different element altogether. So yes, you are right. There are multi-component plasmas, and that's why I call it very complex. It's a very complex system.
Okay, Deva Bhatta and Arijit.
Yes,
It
yes,
was such,
Aureli. Go ahead.
it was such an amazing talk that it was so much inspiring for me. I got a question.
Sure.
The question is actually, what is Valen and radiation belt?
This is very, it stumped me. So I will apologize not only to Arjit, to everybody. I wanted to make an amazing talk with amazing pictures, and my slides, the whole slides crashed. PowerPoint crashed. I had issues with my computer 15 minutes before the start. So I'm sorry. I mean, I emailed Manosh like very in a state of panic that I might be late. So I just pulled together something, And I had pictures of, more detailed pictures of the ionosphere, the Van Allen radiation belts, the magnetosphere, and stuff like that. But so Van Allen was a research scientist, like a researcher, and I forget, I might be wrong, but in the 1940s and 50s, when doing experiments on telecommunication satellites, he found that there are these domains around the Earth. There are actually two locations around the Earth where it's from all his measurements and calculations, it seems that there must be these belts surrounding the Earth where the number of ionized particles are very high. And now we know it's true. So the Van Allen radiation belts is a part of this whole. There are different surfaces. There are different things around our Earth. If this is I don't know if you can see my hand. I mean, I don't have a picture for Van Allen radiation belts in my slides in this set, but there are different layers. And you have the ionosphere and the magnetosphere, which is surrounding the whole Earth, and two domains. There are two domains around it where you have this extremely strongly ionized, like concentration of ionized particles. And so those are the Van Allen radiation belts. I can send you more details. Actually, I would. I'm thinking what might be the best way to do this. I might send an email to the organizers, Manoj and Shri, with some links to all the questions, with possible answers to the questions that you are, and they can
Yes, sir,
probably.
that would be great. Actually.
Yeah.
Debavartha
Because
also has so many questions. Debavartha, please go ahead and mute
go ahead.
yourself and ask.
Thank you, Arijit. Thank you, Arijit.
Yes,
Just
sir.
the ask
Sir,
question.
is plasma made of antimatter?
So plasma, now very important question. And as I said, every question has multiple questions in it, right? So the plasmas I talked of today, the examples I gave you, are not made of antimatter. These are all standard matter as we understand. Now the thing is, you question what is antimatter, right? Antimatter it has the same mass as matter. Say if I want to look at the antimatter of electron, the antimatter of electron is positron. And what are the characteristics of positron? It has the same mass, but the opposite charge, right? So in CERN, you can actually make antimatter, but see, it's the same mass, but a different charge. But see, in plasmas, as we study plasmas, we know how to deal with electrons. We know how to deal with ions. We know how to deal with charged particles, positively charged and negatively charged. Now, so we know how to work with, how to investigate, and how to trap, and how to study and investigate positive electrons. So we know positrons. So if you are studying positrons, if positrons and antimatter is something you really love, again, you will fall back to actually these exotic plasmas are called non-neutral plasmas, because these are plasmas with only electrons or only positrons. So positron plasma is a thing that is studied in CERN and different labs in the world. UC San Diego has a lab, and there's a lab in UC Berkeley. Now, using positrons and if you can make antimatter out of plasmas and trap them and study them. And again, I might send a couple of links to the labs that study like positron plasmas, for example. So you can have positron plasmas, just that I did not, in all these examples of the star and astrophysics and the space and solar radiation, solar systems, these are all regular matter.
Okay. So should I wrap up now? I think there are a lot of questions in the chat box. Small questions.
Yeah, go ahead, and if you can collect the questions, I hope the chat box doesn't go away as soon as you close it. Feel free to.
I will take care of that. Okay.
Yeah, and I might not reply to you in a day. I'll take my own time. I'll take my own time, but I will.
Yes, sir, no problem.
Yeah.
Okay. Thank you so much, sir. Thank you.
Yeah, and it's I would say it's wonderful being with you guys. It's wonderful. And there are so many things I wanted to say, but time is so limited in the whole field of thermonuclear fusion.
No, sir, it's great actually. That's motivation and that inspiration things is you already done. So don't worry that.
Yeah. Thank you.
Okay, sir. Thank you, sir.
And be in touch. Definitely be in touch. If you have any questions, I'll be happy to.
Okay.
And
May I go for the last one? May I go for a last question? Just
I have time for it.
Yeah, no. Actually, the thing is, may we collect plasmas from out of Earth and use it in our daily life? That will be a free energy for us.
nothing is free, or is it nothing is free? How would you collect and how would you bring it? The process of collecting, will it still remain in the plasma state? Or, see, it's like asking, can I connect snowflakes up in the atmosphere, right? Imagine, I mean, just imagine, can I connect snow which is really up in the atmosphere in the clouds and use it in my freezer? But to bring it down, by the time it will melt, so there's nothing free energy, you will have to work, we will have to work and spend energy in whatever we want to do. A much easier way, that's why a much easier way is you take gas, you put some energy and make it plasma. So we make it in our labs all the time. So whichever is easier, basically. It's a great idea, though. It's a great concept.
Thank you.
But
Thank you.
Sir, how is the whole universe 99% plasma?
basically what happened, the well I is the whole visible universe. The thing is, whenever you see something, you can imagine why do we see something, right? We see something because light comes out from it. How does light come out from something, right? It's because electrons go to higher and higher energy state, and when they come back to the lower energy state, it emits the light. It emits photons, right? It emits electromagnetic radiation, and we see that light. So everything that you see must have energy state, will be in a higher energy state. And it happens to be that most of them are ionized. Most of them are in an ionized state. And as the electrons in that ion come back to its ground state, it's emitting the light. So all the stars, all the galaxies, the birth formation and of stars and the sun, everything that you see that emits light, almost everything. That's why it's 99%, not 100%. There's the 1% difference. But everything that you see, almost everything that you see, 99%, is in the plasma state, right? So it's not Y, it's like that's the natural state. It's Y. There's always Y, but that's why it is, because it's that energy of the system that allows the system to emit the light, and that's what we see it. Hence, it is visible. See, here I am not talking about something called dark energy, because we don't know much about it. Dark energy, dark matter, because they don't emit light. So it's the 99% of visible universe. And if you ask that, what's that one extra percent? That 1% could be, a flame of a candle, the light that comes out of hot, excited neutrals. Neutral gases can also get excited to those chemical regions, like the regions of chemistry and chemical energy, where it is not yet ionized. Now, it can emit light. Excited neutrals can also emit light. That would probably be 1%, I guess. And the rest is plasmas.
Okay, guys, actually, we are running out of time. We will go for the dinner. Some of us are there to go to dinner. So, sorry about that. I will send all questions to sir. And then, whenever I will get answers, I will upload it. Okay, thanks a lot, sir.
Go for it. Yes.
Okay.
Good night.
Good night, sir. Good night.
Yes. Good night.